Join me on a journey to the 2024 NASA Innovative Advanced Concepts, or NIAC Symposium, this week on Planetary Radio. I'm Sarah Al-Ahmed of the Planetary Society, with more of the human adventure across our solar system and beyond. Space agencies are well known for creativity, but the NASA Innovative Advanced Concept Program takes it to a totally different level. It funds imaginative and sometimes quirky ideas that could one day change the face of space exploration. I had the pleasure of returning to the symposium to host the webcast this year, and over the next 2 weeks, I'll share some of my interviews with the people I met at the event. We'll kick things off with an introduction from Pam Melroy, NASA's Deputy Administrator, followed by Thomas Swick, Chief Technologist of NASA's Jet Propulsion Laboratory, who will discuss some of NASA's most impactful innovations. Then we'll learn more about 2 NIAC Phase 1 projects that could help us study distant planets or reach them ourselves. Marshall Eubanks from Space Initiatives Incorporated and his colleagues will introduce us to their concept for a swarm of laser-sailing pico spacecraft that could travel interstellar distances. Then Ryan Sprenger from Fauna Bio Inc. joins us to discuss how hibernation could help humans reach other worlds. We'll close out with our chief scientist, Bruce Betts, as he joins me for What's Up and a new random space fact. If you love Planetary Radio and want to stay informed about the latest space discoveries, make sure you hit that subscribe button on your favorite podcasting platform. By subscribing, you'll never miss an episode filled with new and awe-inspiring ways to know the cosmos and our place within it. The NASA Innovative Advanced Concepts program is pretty unique. It nurtures ideas that could potentially transform the future of space exploration. While seeming like science fiction today, these concepts are grounded in scientific and engineering principles. Not all of them succeed, but many have the potential to change how we explore space and create new technologies with applications here on Earth. NIAC funds projects across many areas: space telescope concepts, lunar bases, new systems for sustainable settlement on Mars, spacecraft propulsion, and even astrobiology. The program operates in phases. Phase 1 focuses on proving the theoretical groundwork for a concept, ensuring that the idea has the potential to overcome all the significant technical hurdles. Phase 2 involves developing more detailed designs, conducting experiments, and proving key technologies. And then there's Phase 3. For exceptional concepts, this last round of work focuses on bringing these futuristic visions closer to reality, potentially transforming them into full-fledged NASA missions. Part of what I love about the program and about the symposium is that NIAC emphasizes a collaborative approach, bringing together some of the brilliant minds in academia, industry, and NASA centers to address some of the most difficult aspects of space exploration. Day 1 of the conference began with this address from Pam Melroy, NASA's Deputy Administrator.
Hello, I'm NASA's Deputy Administrator, Pam Melroy. It's my honor to welcome you to this year's NIAC Symposium. For years, NASA's Innovative Advanced Concepts program has encouraged us to push the boundaries of what's possible, turning science fiction into science fact. This program is essential to our agency as it nurtures visionary ideas by supporting early-stage research, while also engaging America's innovators and entrepreneurs as valuable collaborators in the journey. Our next steps and giant leaps rely on the innovation of agency and industry minds, and the concepts born from NIAC can radically change the future as we venture farther than ever before with NASA's Artemis missions, while also keeping an eye on our home planet for the benefit of all. One example of that is the Mycotecture Off-Planet Project, which received NIAC Phase 3 award funding this year to continue its development. Led by Lynn Rothschild and the team at NASA's Ames Research Center, this project is developing technologies that could grow habitats on the Moon, Mars, and beyond using fungi. Not only does this technology have the potential to revolutionize the future of deep space habitats, but it's already being put to good use right here on Earth as potential building material for sustainable and affordable housing in places with scarce resources. I share your excitement to explore new ideas, learn from the best and the brightest in the industry over the next few days. Thank you for joining our journey to the stars. for this year's NIAC Symposium.
Pam mentioned Lynn Rothschild's work. Lynn and her teams are the first to have been concurrently awarded funding for a phase 1, 2, and 3 project. It's really impressive. She's already agreed to come onto the show on a later date to speak about the intersection between evolutionary biology and space technologies. Shortly after Pam Melroy's introduction, John Nelson, who's the NIAC program executive, took to the stage to introduce the next guest.
We're going to kick off today with a welcome from Tom Swick from JPL. We're, of course, right down the street from JPL here in Pasadena. Tom is currently the Chief Technologist at NASA's Jet Propulsion Laboratory. In this role, he provides strategic leadership for the technology development efforts at JPL. And specifically, he's responsible also for the portfolio of projects that fall under the Space Technology Mission Directorate, which of course includes NIAC. Tom's been at JPL for over 30 years. He's worked as the Associate Chief Technologist. He's managed the Space Technology Office. He's worked in several development areas, developed several flight hardware systems, and also led formulation of the NASA Aquarius mission. So it is my pleasure to welcome to the stage Dr. Tom Swick.
Thank you, John. It's a real pleasure to be here and welcome you to Southern California and JPL Caltech here in Pasadena. I'm Tom Swick again. I'm the Chief Technologist JPL and have been working with NIAC and various technologies for many years, as John mentioned. And one of the things we do is assess the health. Well, how healthy is this area for new ideas? Because these are the ideas that pull us into the future. And when I look at the NIAC program year after year, you see it's very healthy. The ideas are incredible. When I look at NIAC, also NIAC's about changing the future. So I thought about that. What are 3 things that we in NASA, and specifically here through JPL, did to change the future? And I looked back and I said there was Voyager, Sojourner, and Ingenuity. And these, I thought, were actually not NIACs. They're either too early or they didn't fit into it. But I was talking to Walt and STMD, and we believe Ingenuity actually was an early NIAC concept. And if you look back, Voyager in 1966, some navigators, some scientists said, every 175 years, the outer planets align such that if you launch, one vehicle could actually travel to all 4 of them out there, Jupiter, Saturn, Uranus, and Neptune. And from that idea, from that simple little idea of astronomy and navigation and trajectory design, Voyager was born. Voyager, of course, still flying. One-way light time, 23 years now out of the solar system, and we still keep, it's plutonium that's driving it, and after this time, the plutonium's down. I think it's a little less than half the power just because of the decay of the plutonium after 72 years of half-life. And so we keep it moving along, finding the faults that come up every once in a while, if you saw that recently, and then figuring out how to fix them 23 light hours away. And Voyager, and of course the golden record on there, which sort of changed science fiction, or originated a piece of science fiction with the golden record of Dr. Sagan and his team. Sojourner in the 90s, it was thought that mobility at the time, planetary mobility from a scientific viewpoint, thought, well, it's not really necessary because if you have a fixed lander, you're going to land in one spot, you're going to have a lot of power and scientific instrumentation on your lander, and so if you're going to scoop and dig and do remote sensing locally, it's probably not much of a gain to be able to rove, say, hundreds of meters with the reduced resources that you could put onto a rover. And so it wasn't a given that rovers were important scientifically, but in fact a group of people had an idea that it is. You can put enough resource onto that rover to drive it around and then put instruments on it that you could make smaller and actually prove that out. So Sojourner, July 4th, 1997, landed on Mars. The actual rover there, as you see, coming off the landing egress system there out to a rock on Mars, was literally built on the cheap. It was Radio Shack parts, for those folks that still remember Radio Shack. We actually, JPL engineers went down the street literally in La Cañada, and had got some parts and screened them and did the right things to try to make them work. But that's how, the ingenuity, the inventiveness came along to show now that roving on planets is important, and that, of course, today we're not going to fly anything but rovers to the planets. And then, of course, our little helicopter ingenuity. Again, an idea. The first idea was simply, can you even fly on Mars? 1% atmosphere by pressure compared to Earth. And so can you even put together the lift, the power, the batteries, some type of control system to allow you to fly on Mars? Because we believed, some folks believed, that if you could do that, you're going to go to places that you wouldn't go otherwise. Even the most, optimistic rover, and you will land and you could do some in situ measurements rather than only remote sensing measurements. And so Ingenuity, of course, landed in 2021, was going to fly for maybe 5 different flights to prove it out. And sure enough, after 72, it kept flying until finally at the end it came down and fell over and broke a blade or two. Is impossible and change of the future that is, and there are many ideas now for other flights on Mars. Probably what actually may even be more important than all that is the use of COTS parts. So Ingenuity is all driven by electronics that are COTS rather than the big heavy RAD 750 and compute and so on. And you need a lot of compute for flying autonomously, such that you could move hundreds of meters and then be able to land in a safe spot and keep your track along the way and so on, when you don't have GPS, obviously, and global localization along with it. And so there's a selfie of perseverance and ingenuity and the changes that bring. Again, small group of people, idea, passion, said, we believe this is really going to change the future. And here are 3 cases that actually did.
I interviewed many of the NIAC fellows during my time at the symposium, but the 2 projects that we'll be hearing about today address some of the questions that I've had since I was a child. How can we send spacecraft to other star systems? And how can we make long-term space travel safer and more palatable for those who want to visit places like Mars? We'll tackle the first of these questions next with Marshall Eubanks and his team. Marshall is chief scientist at Space Initiatives Incorporated, a startup that focuses on developing and deploying small satellites for low Earth orbit. Their NIAC project explores using swarms of spacecraft propelled by laser sails to reach the nearest potentially habitable star system, Proxima Centauri. We have Marshall Eubanks from Space Initiatives Incorporated, along with several other members of the team. Could you please introduce yourselves?
Robert Kennedy of the Institute for Interstellar Studies, U.S.
Andreas Hein from the Initiative for Interstellar Studies and University of Luxembourg.
I'm Paul Blasi with Space Initiatives Inc.
So your project is called Swarming Proxima Centauri. Yeah. Essentially what you're suggesting is that we want to get to the nearest habitable world, well, potentially habitable world to Earth, using not just one, but a swarm of pico spacecraft. How small does the spacecraft have to be in order to qualify as a pico spacecraft?
Well, there's the mass and the size. So the mass has to be a few grams, 4 grams maybe. The size is 4 meters, and so it's not as particularly small in terms of size, but it's small in terms of mass. And that's all set by the size of the laser beam. The laser beam has to illuminate it for as long as possible. So from the laser beam parameters we have, we needed 4 meters.
So what they're trying to do is not just send a bunch of small spacecraft, but they want to put solar sails on them in order to get this technology out using lasers, right? And laser sails, this is a whole extra thing. Usually when we're using the light of stars to do this, it's not as much radiation pressure, essentially. If we really want to get out there and start going at speeds that are close to the speed of light, we're going to have to use laser technology in order to do this. How many spacecraft are you going to need in this kind of group in order to achieve this? And why is the swarm technology the one that you want to be using instead of just sending one really robust solar sail, for example, or laser sail?
Well, the current plans are 1,000 sails. And that's a lot, yes, but we think that with the laser system we have, and there'll be a duty cycle where it sends one and has to wait a little bit, sends one, and we think we should send them all within about a month. And the month comes from getting them to cohere as a swarm after you send them. You'll only have so much. That uses interstellar medium drag. You think of the interstellar medium as a good vacuum. It's way better than any vacuum you could make here on Earth. But at 0.2c, at 20% of the speed of light, you actually have significant drag, and we can use that drag, but only so much.
Why would you want to send more than one spacecraft instead of just one?
Skip some of these.
To avoid single point failure, right? So that's why you don't send one big thing. And the other reason to send many little ones is economic. The human race is unlikely to build this century a laser big enough that'll push anything more than a few grams. It's unlikely to build a laser that big. So you're limited, each bullet, 4 grams, that's it.
We started out really trying to solve one problem, which is how to get enough data back to Earth. But in solving that, and the way this happens sometimes, we realized that actually there's a lot of other things we can do with swarms. And resilience is one of them, but there's a lot more that you can do. For example, we can take pictures of the planet from all sorts of directions. So we can get a map of the whole planet, and not just like wherever the spacecraft happens to look, because we have lots of spacecraft.
Which brings me to my next question. You were already talking about the fact that our laser technology is not yet at the level that we're going to need in order to do this. There are several other components, including the light bucket for collection of the actual data back, that we still don't have in place in order to do this. So what is the current state of this technology, and what advancements are we going to need in order to make this viable?
Actually, the technology exists. It's mostly an economic problem. The launch lasers are variations of like an industrial cutting laser, and some of the military lasers used in beginning to be used in beam weaponry. So the laser technology is available. It's mostly a matter of scaling it up. We're talking for a fleet like this about 100 gigawatts. So it's not just the lasers. How do you power the silly thing while it's sending these guys out? We have a pretty good handle on the technology for building the probes, but they'll probably have to be built in space. They're essentially 4-meter diameter integrated circuits, built using very thin film technology, so they'll be very fragile in most directions. They'll do like 10,000 Gs while they're accelerating, but that's a known force from one direction. And then, like I said, the light buckets on the receiving end, again, that's known technology. They're just big telescopes, but again, you've got to have several thousand of them spread out over a kilometer. Frankly, we anticipate doing this on the far side of the moon. We have to build up that infrastructure.
But thankfully, we're sending humans back to the moon fairly shortly, fingers crossed for the Artemis program. And we've seen other nations. China has already gone to the far side of the moon and done a sample retrieval. So we're beginning to have this capability. So that's totally viable given enough time. The thing is that if we're going to be going all the way out to the nearest potentially habitable world, that's a little over 4 light years away, which means if we did get there, you're going to have a time delay of about 8 years between Earth sending a signal there and then beaming it all back. So you're going to need a fair degree of autonomy in these craft in order to make this work. What kind of decision-making power would you have to be giving each of these spacecraft in order for this to work?
Yeah, so the decision-making power on each of the spacecraft has to be fairly significant, but we anticipate that on the timescales where we expect those other technologies to mature and the economic conditions to be available to develop such an infrastructure, that the computational power available on each spacecraft has vastly increased compared to the current status. So that's the reason why we don't really worry that much about the computational capabilities and the algorithms which are going to be on those spacecraft, because both are making tremendous advances at the moment.
It sounds like you need a very specific kind of formation of these spacecraft in order to optimize this. I was reading about how you want to organize them in kind of like a lens shape, essentially. What is the benefit of doing that?
Well, for all of this to work, they have to be synchronized. They have to communicate with each other. They have to know the range to each other, the distance to each other, so they can determine their positions. And a hexagonal pattern is very good for that. Now, if you only had one layer, you would have a very hard time determining, like, does the thing have bends in it? Is it like a carpet that sticks up or something? That can be hard to determine in the carpet. So you want several layers because we really need to know a 3D position for the whole swarm. And that's crucial both to get there properly in the usual navigation problem, but also to send the data back to Earth in a synchronized fashion. And we think we can get about 1 kilobit per second back with the current plan. And that would mean, that's comparable to New Horizons. So that would mean 3 or 4 gigabytes in a year. And that's more or less what New Horizons sent back. So all the pictures of Pluto, we think we could do that at Proxima Centauri. And by the way, we're assuming that effectively there's no communication from Earth to the probes because of that. Because any data from the Earth of Proxima itself will be 8 years old. Right, from the probe standpoint.
They're on their own.
They're really on their own. They have to decide all of this stuff and do all of this stuff, and and even like pick out which will take way more pictures than we can send back. So they have to decide which pictures we can take. And in fact, I call this the Paris selfie problem. You have 1,000 tourists, you get them all a camera, and you say, go to Paris and take a picture, and you get back 1,000 pictures of the Eiffel Tower. That's not what you want. You want, distribution. So that's actually a fairly tough computational problem, but we do have a lot of probes. So not only has each probe's intelligence improved, or computational ability improved, but we can also use them as a swarm together, and so you can have a distributed intelligence, and that we'll be doing a lot of that of necessity, because we can't even send all the data we collect between all the probes, and so you have to say, here's my best data, what's your best data like? We got to have, and then come up with a coherent picture of what's the best data for the whole mission to send back to Earth.
And I guess that's the benefits of a mesh network. You can interconnect all of them and really do this kind of science. But given the really limited nature of how much mass you can put on these, what kind of instrumentation can we actually hope to send to Proxima B with this technology?
Oh, we're planning a lot. We think we can do 60-meter resolution with the best. So I mean, that would mean, for example, in terms of like looking for technosignatures and biosignatures, we could look for airports. We could look for forests. We could look for, coral reefs, maybe, that kind of stuff. There's a lot you can do with imaging. I mean, we've heard from people, anything you can do up there with these small probes, you could do on the Earth. Well, no, there's just no way. I mean, we could look for lightning on the dark side. We will go by both sides, and so we could look at the dark side and the light side. And from a biosignature point of view, the most important thing, I think, we can do transmission spectroscopy. So we can look at Alpha Centauri AB set behind the planet, for example. We can look at the sun set behind the planet. We can look at the drive laser, if we can get the drive laser turned on at the right time, set behind the planet. And from that, you can find out a lot about the planetary atmosphere and what molecules are in it. So you could look for methane or carbon or water or, ozone, all kinds of different molecules, some with photography and others with transmission spectroscopy. So if you combine those two things together, I think you have a really powerful quick look. I mean, it won't, if you saw the video we have, it's your 30 seconds and it's over. A long time to be gone and a short time to be there, but because it's a 20-year voyage. But we think we actually have a good chance. If there's a significant biology or technology even on Proxima B, we should find it.
That is the dream right there. We do have the technology with many of our spacecrafts to look at the atmospheres of other worlds and analyze their components. That can give us a good idea of whether or not they're habitable, but the ability to actually send our instruments to another star system and analyze that world up close, that is so far beyond anything we're capable of right now, and that could change everything, not just for Proxima B, but what other applications could we use this for? What other worlds could we explore using this technology?
Well, clearly we're going to have precursor missions, as one of the other speakers was talking about. We could send, my visioning is we'd first send missions to nearby asteroids, potentially hazardous asteroids maybe, to look at them. This would be a very good capability for the Planetary Defense Office to have. If we find a new potentially hazardous asteroid, send a few probes out there. What does it look like? How big is it? What's it spinning like? All that kind of stuff. But then you can just go, and so I think it's a step program. You'll do that. You'll go to things like, the Martian Trojans. We could go there. It's as easy as getting to Mars, but nobody goes to the Trojans because, you're going to go to Mars instead of the Trojans. But we could, because they're cheaper. So that's another advantage. It's cheap. But then as you develop capabilities, you can go out. With a fraction of the power the laser would take to go to Proxima Centauri, targets like Sedna, 100 AU away, Eris would become quite possible. You know, it would not be, oh, it's way out there.
40 years.
You don't have to wait 40 years. You could do it, well, in a year at least. I mean, at worst, you know, it's like all these things you think about, you could get there within a year mission. So that actually makes it more like a grad, you know, if you want to think about it, the academic aspect, it's like a grad student could like, oh, I want to send a mission to Sedna, get the data back and get their PhD, all without, you know, growing a long gray beard.
And I liked it that in your original article on this, you pointed out that you could not only do things like that, but potentially even use it to go to places like interstellar asteroids like Oumuamua and things like that. That, you know, we've seen a few of these things. I think 2 interstellar asteroids go through our system. That one and Borisov came through, and we had no way of getting to them in time to investigate them. With this technology, we just go right out there and check it out.
Well, actually, there is a way to get to them with a funny, you know, solar flyby and later Jupiter flyby, which most of this team was in on. It's called Project Lyra. You're looking at 3 of the authors. You know, people think we missed the boat on Oumuamua. We didn't. We could catch it. And with lasers and laser sails, you could absolutely fly by Oumuamua.
One of the things I like to say is for millennia, for thousands of years to come, getting to Oumuamua will be easier than getting to Proxima Centauri. I think we will go there eventually. The question is, will it be in 10 years or 100 years? But eventually somebody's going to say, yeah, we should go out and look at it. And as this technology improves, doing that's going to get from, I mean, we could do it right now if you wanted to devote like a whole SLS launch to sending a fairly small 100 kilogram or so probe to it and do a lot of gravity assist and so on. And, you know, it would be expensive, but, you know, if you wanted to, you could do it. As this technology improves, that'll get cheaper and cheaper and quicker and quicker. At some point, somebody's going to say, well, you know, let's just do that. It's a 5-year mission or a 1-year mission or whatever, but, you know, we're doing all this other stuff. We might as well do that too. So I'm convinced of this. We will get to Oumuamua one of these days. And that is even true if we find a whole bunch of other ones, just because it'll be the first and it's a little strange and it's not, from an interstellar standpoint, that far away.
And to actually touch an interstellar object, touch or sample it on the way past, that's worth a flagship mission. 10 to the 10th of dollars. The value to science, that's absolutely worth that kind of money, like we paid for great observatories or flagship missions. It's genuine, bona fide, extrasolar origin. That's worth knowing, paying a lot to know.
I absolutely agree. I mean, can you imagine just the amount that we're learning about our place in space through samples like OSIRIS-REx, through the Hayabusa missions from JAXA, like the far side of the moon sample. I cannot wait to see more about that. It is absolutely bonkers what we could learn. And if we could get a sample of literally material from another star system, who knows what that could teach us about ourselves and our place in the universe. I think this is really cool technology, and I'm really glad that organizations are doing this. You're not the only ones that have proposed trying to go to nearby star systems like Proxima using this. But I mean, as someone from an organization who once had a solar sail, we get emails every week about people who are passionate about this. So I really hope that your team manages to pull this off and move on to the next phases, because this is revolutionary. This is game-changing stuff. Well, thank you so much for joining me, all of you. I really appreciate it, and seriously, all the luck in the world from the bottom of my heart. This is the dream technology I've wanted to see since I was a small child, and I'm sure that's true for all of you as well. That's a nerdy thing to say, but it's true.
Well, I think you made my day.
We'll be right back with more from the NIAC Symposium after this short break.
Greetings, Bill Nye here. NASA's budget just had the largest downturn in 15 years, which means we need your help. The U.S. Congress approves NASA's annual budget, and with your support, we promote missions to space by keeping every member of Congress and their staff informed about the benefits of a robust space program. We want Congress to know that space exploration ensures our nation's goals in workforce technology, international relations, and space science. Unfortunately, because of decreases in the NASA budget, layoffs have begun. Important missions are being delayed, some indefinitely. That's where you come in. Join our mission as a space advocate by making a gift today. Right now, when you donate, your gift will be matched up to $75,000 thanks to a generous Planetary Society member. With your support, we can make sure every representative and senator in D.C. understands why NASA is a critical part of U.S. national policy. With the challenges NASA is facing, we need to make this investment today. So make your gift at planetary.org/takeaction. Thank you.
Later that day, I spoke with Ryan Sprenger, senior research physiologist at Fauna Bio Inc. Their company focuses on AI-driven drug discovery. It uses data from the last 100 million years of evolved disease resistance in mammals to find new ways to improve human health. Their team's NIAC proposal looks at animals that naturally hibernate to learn more about how we can induce a state of torpor in humans for long-term spaceflight. Thank you so much for joining us.
Happy.
So this is Ryan Sprenger, correct?
Yeah, I like Jerry Sprenger.
He's from Fauna Bio Incorporated with a project called STASH. Now this is studying torpor in animals for human space health, or
space health in humans.
Space health in humans, yeah. Essentially, if you're a fan of science fiction, you've probably heard of this idea of putting people into a hibernative state or a cryogenic freeze, as an example, in order to send them to other worlds, right? Cryogenic freezes, we're not all the way there yet. Completely freezing humans is not the thing, but what is it that you're trying to do here in order to enable humans to travel to other worlds?
Yeah, essentially what you're talking about, we're interested in studying hibernation as a potential way of traveling humans in space for longer and in a healthier way. And so based on precedental information that we have from the ground, we know that hibernators are protected against a lot of things that you run into in space. And so that's where the health benefits come from. And these are things like radiation. For example, hibernators are well protected against radiation. They don't have disuse atrophy, so they don't lose muscle on the ground when they're not active. And these are two major health risks for astronauts in space. So that's the health aspects of it. And then in addition to that, like you had mentioned with the science fiction and the cryopreservation, long duration space flight might be a lot easier if you're in a semi-quiescent state like hibernation, where you're not perceiving that you're in space for years and years and years. And on top of all of this, hibernators don't eat, drink, they don't go to the bathroom. These are all things that you have to think about when you're traveling very far or in space for a long time. And so if you can move humans, for example, into a state like that, you have a lot less issue with logistics with regard to that long duration space travel. So there's a lot of benefits that hibernation may provide to astronauts in space.
I'm thinking, too, about the psychological impact of being stuck inside of a spacecraft for that kind of extended travel through space. There's a lot of studies we've done on trying to lock people into these tiny little biocontainment units and see how they all interact over time, but it might be a lot healthier and a lot easier if we can just kind of put people into hibernation. The question is, how are you planning to achieve that? Because we want to do it safely and make sure that we can do these studies in a way that's ethical.
Yes, yeah, and that's what STASH is starting with. So the question is, how do you safely translate hibernation into humans? And that's something that you can work on the ground, for example, but translating hibernation into humans in space is a whole different question. And so STASH, for the first time, would allow for the actual study of hibernation in space, which has not been done ever. So we don't even know if hibernation will work in space. We don't know if the protective mechanisms will still be happening in space. And so STASH is providing an environment that you can study hibernation in space for the first time. And as a consequence of that, we can also study other organisms in space as well with regard to real-time physiology, which again is not currently available in the space environment. So that's the first step to doing it safely, is first understanding what it looks like and how it applies in the space environment. And then from there, applying it into humans, again, is a very precarious road to take, but it is a road I think that we do need to take. But doing that safely, that's a large discussion, maybe for a different time.
And we're not just talking about launching one of these random units into space, right? We're specifically talking about putting one of these on the ISS and on the International Space Station. And specifically, you want to integrate it into the SABLE unit, correct? I'm forgetting what the acronym stands for.
Space Automated Biological Laboratory. That's developed by BioServe, and they're in Colorado Boulder. But yes, so this is aboard the ISS. It's already there. We've actually, as part of our program, we've shown integration efficacy with the SABLE already. So the unit that we're developing as part of the STASH program is called the Respires unit. We've just named that recently. And so this would be launched and integrated to the SABLE onto the space station to allow for this study.
So how do you actually induce this hibernative state?
Yeah, it depends what you're trying to induce it in. In a natural hibernator, you really don't have to do anything, to be honest. They'll just do it by themselves when the season or the time of season comes around. In an animal that doesn't normally hibernate, there's a couple different methods that you can induce it with. Typically involves sort of messing with the preoptic area of the hypothalamus. The field is now sort of at the point in which we can induce a hibernation-like state in, for example, a rat, which normally wouldn't hibernate. So that's a different induction method, but for our purposes, we just have to put them in the right time of season, and they'll go into hibernation. We think. At least on the ground they will. We don't know in space yet because we don't know how well hibernation will work in space. But the most robust way of inducing, though, is making the environment cold. And so that's also what the Sable provides, is environmental control. So the Sable can move the temperature of the unit down to about 4 degrees, actually down to -5, but we won't go that low. So you make them cold. They won't eat at that time of year. They refuse to eat, despite giving them food and water and everything like that. They won't eat. And so it's quite an easy induction with the species that we're looking to study first.
I mean, forgive me talking about hibernation. I'm immediately just imagining bears in space, but we can't fit those on the ISS, unfortunately. So,
and I'm glad you mentioned that, because the best species to study for human hibernation is bears. We think that human hibernation will look a lot more like bears than it would, for example, a hibernating ground squirrel or a small rodent. So that would be the dream: is bears hibernating in space, which would be cool. Yeah.
Since we can't accomplish that, though, what are some model organisms that we can use that have enough of similarity with humans that it's meaningful science?
So the species we use is the 13-line ground squirrel, and the reason we use it is it's the only hibernating species that's bred in captivity. It's the only hibernating species that has a complete genome. So it actually has the tools necessary, or the readiness to translate into humans. And Fauna Bio actually uses this species quite frequently to translate other drugs and targets into humans, and we've been quite successful in that so far. And so this actually turns out to be a really nice species to have meaningful impact in humans, because we have that complete genome. And we've had some success in developing targets based off of this species. So it has enough of a shared genome with humans that it's translatable. There's other species that would be great, like bears. And obviously the 13-line ground squirrel is a rodent. Having a primate would be the best. And it turns out there is a primate that does use hibernation or torpor called the ring-tailed lemur, but it's wildly endangered and not a species that you can use to study something like this. Yeah.
It makes me really glad to hear that you're starting out with animals that already have hibernative states. I think that solves a lot of the ethical considerations around whether or not we'd be doing harm to animals that don't naturally hibernate, right? But that brings up the whole next question, which is, how do you deal with the potential ethics of freezing humans for that long and what that technology could mean?
Right, and this is where that precarious nature of translating into humans is going to come, because there will be challenges associated with this translation into humans. Now, our first step, we think the best thing to do is to first look for targets, druggable mimetics, for example. So pathways in the ground squirrel that are upregulated during the hibernation in space, and saying, okay, is this what they're using to protect themselves? And can we translate that into a drug that you would then give humans might afford them those protections? That's step one, we think. Step two is, and we think it's important, step two is actually moving humans into a torpid-like state because of all the other benefits. That is going to be a long, arduous process. There's a lot of things that you have to avoid with moving into a lower metabolic rate, a lower body temperature. There's issues with that. For example, in extreme hypothermia, obviously humans run into cardiac arrest, respiratory arrest, and total organ failure. And so being able to avoid that is going to be key. And that's why we think bears are going to be a better model, because they don't go as low in body temperature, they don't go as low in metabolic rate, but they still have substantial savings, and they still are in this quiescent-like state, and their organ systems still function. And so there's going to be different ways to approach it safely, but eventually we'll have to move into some sort of human testing in the future. Yeah.
Assuming this goes all the way to phase 3 and then beyond, right? Cool. It's a really interesting concept, because we all want to be able to send humans beyond our planet to other worlds, but there's so much going on there. I do wonder, though, why is it that a hibernative state on Earth can allow for us to not worry about like bone density loss or muscle density loss, as an example? And do you think it's going to be functionally different in space? And I guess we won't really know until we get there, but...
Yeah, that's a very important question for this kind of study, and that's actually one of the main reasons why we want to study hibernation in space. Is it different in space? Do the protections change? Do the sort of benefits that we see in hibernation change? A lot of the things that we're learning from hibernation have applications, we think, on the ground as well. So it's sort of a dual-use system. We can potentially derive a lot of benefits from hibernation in space, but also on the ground. And so, avoiding disuse atrophy, avoiding osteoporosis, these are things that would be great on the ground. There's a lot of applications for that as well. We hope it's not different between the ground and space, but we don't know.
I mean, imagine if, I just want to sleep until my birthday, and then I can just rest and come back refreshed. Imagine what that can do for our longevity, or say you have a terrible terminal illness and you want to go into some kind of hibernative state in order to allow us more time to grapple with the medicine of that. That's a mind-blowing concept.
It is, and there's actually a really neat anecdote, and I'm forgetting the name of the author, but he wrote a book about his uncle who was in what seemed to be a torpid-like state, and when they pulled him out of the torpid-like state, and this was because he had some issues in his hypothalamus in the area that we think is contributing to the state. When they pulled him out of that hibernation-like state, it actually turned out that he had a cancerous tumor in his lung, and that then multiplied, and he succumbed to the cancerous tumor. So exactly to that story, it might prolong life in more than one ways, making a disease quiescent, for example, like that, or waiting until new medicines come along. And there's tons of other applications that hibernation seems to have on the ground. So for example, Fauna Bio just started a partnership with the Eli Lilly. This is an obesity type question. Hibernators are really good at saying, we want to use just adipose tissue. We want to use just fat as our fuel source. And so in a very targeted way, they can reduce their adipose mass, which is something that we wish we could do. So there's a lot of other benefits that hibernation seems to have just on the ground. Yeah.
What are some of the metabolic processes or things you're going to be measuring in your test subjects in order to see whether or not this is actually working?
Yeah. So the unit that we're designing, the Respires unit, is more or less something we would call a plethysmograph. So this is allowing us to measure real-time ventilation in a free-moving animal. So we can measure how frequently they breathe, how deep they breathe. With that, you can measure metabolic rate too, because it's a sealed chamber. So this is indirect calorimetry. You're measuring oxygen consumption and CO2 production. The animals, we're thinking right now, the best option for the first couple experiments is to add telemeters to the animal, so then we can get things like heart rate, body temperature, activity. With all of these, you can assess hibernation quite precisely. We know exactly when they are entering into hibernation, we know exactly how long they're in hibernation with these measurements, and then we know when they're coming out as well. And these measurements are critical to measuring things like cardiovascular health, pulmonary health, and things like that in vivo, in a free-moving animal. Yeah.
You'll be getting data back from the ISS here on the ground, but are these experiments something that the astronauts aboard the ISS are going to be doing, or do you anticipate bringing the subjects back to Earth for further study?
Yes, we will be getting data. A lot of it will be real-time. So these are the things that are non-telemeter, although we want to develop the unit so that we can get real-time telemeters too, so that gives us heart rate, body temperature, activity, things like that. But the metabolic rate, the ventilation, these are real-time measurements, so we will get that data back immediately, and we can see to the second when these animals are moving in. So that will be happening. So live animal return is very difficult with the ISS right now. It is possible, and it's something that we've discussed with the chief flight veterinarians of NASA as well as the IACUC committee. It's something that we want to shoot for, but the initial mission's probably not. So this would be a tissue return rather than a live animal return. Again, very valuable tissues because we can learn a lot from what pathways and what molecular things changed, that we can start to determine, did they lose muscle? Was there radiation damage? Although in LOE, we wouldn't expect to see a lot of radiation damage. And other pathways, so see what was upregulated in those instances. So for the first initial missions, it will likely be a tissue return, but beyond that, live animal return would be even better. So that's something we're targeting in the future. We are trying to develop the system as autonomous as we can because we want this to be applicable outside of LOE, so that we can start to ask the radiation questions as well. And so we are in the process of developing it to be more autonomous for like Gateway or Artemis type missions. So we try to do that as much as we could for this phase one, making it as autonomous as possible. So for example, it's a self-regulating air circulation system. So we don't have to adjust the airflow for the animals depending on what metabolic rate they're at. So all the astronauts we think would have to do is the integration process, so putting it into the Sable. Per IACUC rules and animal ethics rules, we have to check on the animal every day. So we will have infrared cameras to see the animals, but we've also got viewing windows, so sometimes the astronauts will have to go and view the animal via the viewing window. And then after that, the only other process that the astronauts would have to do is take the animal out of the chamber for the termination of the study, essentially. Yeah.
I know this is really far future looking, right? We're only talking about beginning these studies that we can potentially send people to Mars someday, but the dream is being able to put people in hibernative states so we can someday maybe send ships out to other worlds that aren't generation ships. I know that's far-flung, but this is NIAC. This is what this is all about. Thinking about those ridiculous scenarios and then finding a potentially ridiculous but also viable solution to them. Is that part of the dream and why you became a part of this, or what inspired you to get into this?
Specifically, I myself and my team, we are very much interested in interplanetary space travel, and we think that this is going to be a very usable and critical way of doing it without generation ships. And so that's part of the inspiration, is that we want to be part of the group of people that helps send people into space further. And so that's where our interest comes from, our basal interest, I would say. That's what inspires us to kind of try to push it further. And where we're at on that field, it's really hard to say. How close are we to putting humans into hibernation? I know that Trish has funded 2 studies this year looking at actual human hibernation. So in a rudimentary sense, looking at cellular hibernation in humans, as well as reducing metabolism using sedatives, for example. But we're at the point where we're starting to, I think we're just crossing the start line of trying to apply this to humans. Now, how long is it going to take? Who knows? But we'd like to be part of that process, particularly in the space field, is understanding hibernation in space and then applying it to humans. That's where it's all coming from.
Well, I mean, first, we got to get to the moon. Then we got to get on to Mars. You got some time to work on this, but a little bit of time. But I am surprised we've never begun to do these studies yet, considering how prevalent it is in science fiction. And I'm so glad to hear that you're beginning to do this work and that NIAC is supporting this program.
Oh, yeah, we are too. And I'm actually glad that you brought that up as well. This question has been asked of the hibernation field, I think dating back to the 60s, really. There's been working groups that have been put together by several NASA groups in the DoD, for example, asking, are we there yet? How close are we to being able to test this in humans? And the answer always has been, we just don't know enough. But I do think in the last 10 years, we've really moved into starting to say, we might have an idea of how to move forward on this. And our advancements in translating a hibernation-like state into animals that don't normally do that has gotten really sophisticated, actually, over the last 5 years, I would say, even. So there's been a lot of really amazing progress in the last 10 years in that way. And obviously, that's building off of the foundational work of all the hibernation physiologists coming before. But the field has moved in a really good direction, we think. And being, NASA and NIAC showing it continued interest in this is really encouraging.
There's still so much to come in next week's episode about the NIAC Symposium. One of my personal highlights was astronaut Mae Jemison giving a tribute to our co-founder, Lou Friedman. He's been on the NIAC External Council for quite a while, but this was his last year. In the meantime, here's our chief scientist, Dr. Bruce Betts, in What's Up. Hey, Bruce, I have returned from NIAC.
Hey, welcome back. You made it.
Ain't no party like a NIAC party. I'm kidding. Everyone was, very professional. They do have wonderful after-hours meetups. I have not personally been invited to any NIAC ragers, but, maybe it happens somewhere in history.
Maybe.
But yeah, there were some really good projects this year, but I was really impressed with Lynn Rothschild because she's the first person to ever have a phase 1, phase 2, and phase 3 project all in the same year. Like, no pressure.
That seems counterintuitive.
Yeah, it's a lot. That's a lot of projects going on all at once, but they're all really cool.
Oh, they're different projects.
Oh, yeah,
that makes
all different projects.
So much more sense.
Yeah, I mean, the phase 3 project was about mycotexture and creating habitats on the moon and Mars using basically mushrooms like mycelia to help seal things together. But personally, my favorite project of hers is the mobile astropharmacy, where you can kind of keep little samples of things that allow you to create medicines while you're in space on the fly. That way we can treat our astronauts if they're all the way at Mars without the medicine that they need. I think that's really powerful, not just for space, but also for Earth. Like, how many people need medications they don't have access to?
A lot.
A lot. That's the kind of technology, that's the kind of forward thinking that just really underscores why technology advancement in space really helps people on Earth. I mean, there's a lot of those overlapping technologies. I mean, can you imagine life without GPS or the internet?
Yes.
Yes. I remember the dark times.
I lived a little of that.
Another one of my favorite projects that I spoke to Edward Balaban last year, but again this year because the fluidic telescope concept moved on to its second phase. And not that I want to get into the intricacies of the fluidic telescope, but what I think is really cool about it is that we're finding new innovative ways to be able to launch bigger and bigger telescopes into space, or to find ways to have telescopes that are self-healing, as an example. Because, I mean, let's face it, I don't know how we're going to get anything bigger than JWST into a rocket and launch it into space, unless we're going to find a way to build rockets that are just unachievably large.
Yeah. Well, you got origami, and apparently you got fluidic, and you got people with tin cans.
But But really, though, like, what kind of mysteries are there in planetary and exoplanetary science that would really be helped by a huge, huge telescope or even multiple JWST-sized telescopes in space that we just, like, can't achieve right now?
Sorry, the concept of multiple JWSTs just kind of fried my brain for a second. Doing interferometry with, wow, that's
right.
Okay. Anyway, exoplanets is the first big answer, because just like JWST is allowing us to do more, and hopefully the Habitable Worlds Observatory, often 10 or 20 years, will allow us to really study exoplanets, including ones that are Earth-like, and that's something you just need some monster telescopes with serious resolution to learn more. And so, but there's also the old, we don't know everything that will do for us, because there are discoveries waiting to happen once we can see them. And so that's why every telescope advancement, every spacecraft that goes somewhere with better instruments or somewhere new, we learn stuff. And often we learn stuff that we didn't even know to ask the question. And that's what's cool about it, as well as a lot of other things. Yeah. Science.
I mean, just getting telescope time on something like JWST is really difficult. And I'm sure there are so many people
surprisingly enough
would love to get time, but can't. And like, I think what CubeSats did for space missions, for smaller organizations and universities and people like us that wanted to send things like LightSail into space, right? If you could find a way to allow people to have a cheap kind of foldable, modular, smaller thing that can go into space and then extend, give that technology to a bunch of universities, wow, the discoveries we could make.
Yeah, although it's hard to foresee doing really giant telescopes with that analogy, but they would do more. Maybe if your fluids and your I don't know, what else you got?
I mean, I just think that's cool. You know, make it kind of like an extendo, foldable, origami style that you just put liquid on it, and suddenly you got a big old telescope. I don't know. That's
wait. I want to focus on you just put liquid on it.
I just put liquid on it.
I feel like that's an oversimplification, but
it definitely is.
I haven't read their research, so maybe I'm wrong.
No, you have to have very specific fluids. They can't freeze. They got to remain fluid in certain temperatures. Like, there's a lot of complexity to what they're doing there. But I mean, I guess that's the whole point of these NIAC projects, is that you take these concepts that like seem really sci-fi and out there, and if you can actually make them real, you're not always going to succeed, but those moments where you really innovate and change things, like, that is powerful.
Yeah, powerful.
Well, before we move on to the random space fact, I wanted to share a comment that our longtime listener, Mel Powell, sent in. Because a few weeks ago, you and I were joking about food in space and salads and how we should start a Planetary Society salad dressing company. It was a total joke. But he wrote in and said that he's got the perfect name. Enceladus.
I get it. Enceladus.
Sorry,
That's
I'm
good.
A child. I literally snort laughed, and I said that in our member community. I was like, I'm really glad no one was here to hear me snort laugh during that. And he said he would almost kill for a recording of that. And I would love to tell everyone that I have a bunch of ridiculous recordings of me laughing like the child I am. So
well, you should start a separate podcast that has no words. That's just you snort laughing.
Oh man, that would be a weird ASMR, but snort laughs to fall asleep to.
There you go. Maybe there's a NIAC proposal in there for that. You can probably use the frequencies of the snort laughs to, I don't know. You'll figure it out.
All right. So, before I embarrass myself any further, what is our random space fact this week?
Let me embarrass myself. Thank you.
Random space fact.
So, Europa Clipper, our friend, coming up on launching, doing this awesome mission. The launch mass, that's the dry mass and the wet mass, as they call it, so the fuel and the spacecraft, not the rocket and stuff, the spacecraft and what it's carrying on board of the Europa Clipper spacecraft is about the same as the mass of a large African bush elephant, the largest land mammal on Earth.
Yep, I do not think I could lift that.
No, I don't think. I mean, no. Okay, well, thanks. Anyway, it's big, it's massive, it's Europa Clipper, and it's going to Europa.
And that includes the ginormous solar panels they put on there?
Yes, it does. It's
okay, that makes sense, because I feel like that's most of the
launch mass.
That's cool.
Yes.
It was quite startling, actually, seeing those things on the spacecraft after seeing it as this tiny thing for a while and just like as artistry, little artistic renditions online. But most of those images have a hard time actually showing the entire span of the solar panels on it just because of the angles they're taking it at. They're literally that big.
About the length of a basketball court.
Yikes.
There you go.
Oh, if this thing works. All right.
All right, everybody, go out there, look in the night sky, and you think about names for space salad dressings. Thank you, and good night.
We've reached the end of this week's episode of Planetary Radio, but we'll be back next week with more of the 2024 NIAC Symposium. I'm excited to share one of the amazing projects that hopes to screen water on Mars for evidence of extant and introduced life. If you love Planetary Radio, you can get Planetary Radio t-shirts at planetary.org/shop, along with lots of other cool spacey merchandise. Help others discover the passion, beauty, and joy of space science and exploration by leaving a review or a rating on platforms like Apple Podcasts or Spotify. Your feedback not only brightens my day, but helps other curious minds find their place in space through Planetary Radio. You can also send us your space thoughts, questions, and poetry at our email at planetaryradio@planetary.org. Or if you're a Planetary Society member, leave a comment in the Planetary Radio space in our member community app. Thank you so much to everyone in our member community that asked for a second episode of NIAC. I'm going to be doing some more in-depth interviews with other NIAC fellows in the future, so keep an eye out. Planetary Radio is produced by the Planetary Society in Pasadena, California, and is made possible by our imaginative members. You can join us as we support the innovators that could one day take us to the stars at planetary.org/join. Mark Hilverda and Ray Paoletta are our associate producers. Andrew Lucas is our audio editor. Josh Doyle composed our theme, which is arranged and performed by Peter Schlosser. And until next week, dream big and ad astra.